Here we see a feedback circuit. So the first step is to identify the input and the output. It's seen here that the input is a current source and the output is a voltage source. So this is going to be a shunt type network. After identifying the type of feedback, the next step is to identify the feedback portion of the network. Here we see from the output to the input side, here's the output side, here's an input side, that we have RF is our feedback portion. So to find the next step, which is R11 and R22 and beta, we're going to look at the feedback portion only. To look at R11, we have to look at this side of the network, which is going to be a shunt. So we're going to ground that side, and R11 is going to be RF. For R22, again, we draw the feedback portion, and we look at this side of it. And then we refer back to the type, and it's a shunt. So again, we short shunt and we open a series. We leave it open. So this is again going to be RF for R22. Now for beta, we draw the network again. And for beta, on the output side, we put the type of output it is. In this case, it's V0, so we place V0. On this side, it's a current, so we place a short for the current, and we call this IF. Beta is defined as IF over V0. So putting IF in terms of V0, it's going in this direction, so it's negative. So we have IF is equal to a negative V0 over RF. So to get this in terms of IF over V0, we'll divide here, and this ends up being a minus 1 over RF as the value for the feedback. So now that we have those three components, we can redraw the small signal version of this, removing the feedback portion and placing in now this R11 at the input side, R22 at the output side, and then we use the equations for this beta, which is beta feedback, so I'm going to call it beta feed here, and redrawing this with the small signal circuit. I'm going to short this capacitor, which is large, for this is my input side, so I'm going to place R11 here. The source side is grounded, so remember this is gate, source, and drain. And I'm going to also include RO. And then this is an ideal current source, so that becomes an open. And this is my output side, so I put R22 here. And this is my V0. So from this is my new A circuit. I want to gather three pieces of information. I want to know the gain, which is going to be V0 over IS, which will be my A value, the open loop gain value A. I want to know RI, which will include RS. And I want to know RO, which will include RL. In this case, there is no RL, so my RO will be at this location. And my RI will be here. And then the A gain will be from V0 to IS. So now I want to analyze this circuit. So I need to get V naught in terms of IS. So V naught can be written as a minus the current minus GM VGS times these two in parallel. So RO in parallel with R22, which is RF. So I'm going to just put those values as RF. And here's also RF. Now VGS is a current source in. So I times R will give me VG. And I notice that VS is ground, so VGS will be just VG. Remember that if it's not, you also have to find the VS value and get VGS, which is VG minus VS. So VGS in this case then was IS times RS in parallel with RF. And I can plug that in here and then divide by IS to get V naught over IS, which is my A, as a minus GM RO in parallel with RF times RS in parallel with RF. So now I have my A value. I can also write RI and RO. So RI, remember this includes RS, will be RS in parallel with RF, and RO, which is here, is on the top of the dependent source, so it's going to be RO in parallel with RF. So now I have these three values. I'm going to use the feedback equations with the amount of feedback. For RO and RI, the amount of feedback, whether I divide or multiply, depends on the type of network I have. For shunt type, we're going to always divide by 1 over the amount of feedback, and for series, it's always a multiplication. So since both of these are shunt on both sides, the input side is shunt, the output side is a shunt, they're both going to be divided by the amount of feedback. So AF is going to be A over 1 plus A beta feed, which is the feedback value, minus 1 over RC. So I get A is a minus GM, RO in parallel with RF, RS in parallel with RF, all over 1 plus, again, this minus A, or A, which is a minus GM, RO in parallel with RF, RS in parallel with RF, times the beta feedback, which is a minus 1 over RF. So these minuses cancel and give me a positive term. So this is my AF value, and this is the feedback gain that we'll have for this particular circuit. Now for RI, RIF, this includes RS. I'm going to divide the RS in parallel with RF, which is my RI value, by the bottom of this, which is the amount of feedback. Now this includes the RS. I do not want to include the RS for my overall feedback value. So because this is a shunt type, to remove the RS, the term we used was RN. This does not include RS. We have to take this RIF, and it's usually easier to find the value itself, and subtract off the RS. Because it's in shunt, that means it's in parallel, so I'm going to have to take this as a parallel form. For RI or ROF, it's the same thing. It was RO in parallel with RF divided by the 1 plus A beta feed, and so that's again the same term, GM RO in parallel with RF, RS in parallel with RF times 1 over RF. Since there's no load, RL that we factored in there, this would be also our R out for this case. If we had an RL included in this, to remove it, we again would use 1 over ROF minus 1 over RL to remove it.